Okay, we are on chapter 14. Do a little lecturing, little break, and then I'll have to take the exam later. If I could find a Xerox machine. We'll see. All right, so chapter 14. We were talking about acids and bases, obviously, in this chapter. And remember, there's sort of a list of strong acids. And again, that's HCl, HNO3, H2SO4. HClO4, HBr, and HI. So this list of strong acids are really good to know. Remember, if we want to calculate something like the pH, minus the log of H plus. Similar scale that measures hydroxide, negative log there of the hydroxide concentration. Again, the relationship between both of those, pH plus POH equals 14. In addition, if we do have the pH, we can get directly from it the H plus concentration by the inverse log of the minus pH. And also, if you have the POH, you can also get the OH minus concentration directly from it. Exact same calculation, inverse log of minus POH. Again, inverse log on most people's calculators will kind of look like a 10 and a caret when you hit it as well. We could also, as we talked about last time, still use KW, which is equal to our H plus concentration, our OH minus concentration, and that equals 1 times 10 to the minus 14. So as we talked about last time, it does give you sort of a variety of ways to sort of solve some of these problems depending on which way you go. And if you do have a strong acid or even a strong base, and as we talked about, most strong bases are group 1 and group 2 on the periodic table. Again, lithium, sodium, potassium, hingorite, calcium, strontium, and barium. Any of these guys, kind of with hydroxide in the formula, are usually strong bases. And if you have a formula of a strong acid or strong base and you want the pH, you basically just need to get the H plus concentration, which for most strong acids is pretty much the same as the concentration of the entire acid because they're monoprotic, they only have one hydrogen. And if you're doing something like the base here, you need to get the hydroxide concentration. That will lead you to probably the POH and then to the pH. At the very end, last time we started talking about weak acids. And weak acids are weak electrolytes, like HF, for example. And when it breaks apart, it does not 100% break apart into its ions. It mostly stays together. And because of that, it will set up an equilibrium. And to solve this type of problem for like pH, we have to do an ice table. And again, really the purpose of the ice table is to figure out what is the amount of free H plus concentration at equilibrium. And once you do that, then usually you'll go into the pH. So it's a very similar sort of calculation as we did obviously in the equilibrium chapter. You could do all the same normal stuff, which is you probably won't get a perfect square in this situation in most cases, but you can try your assumption. You could also obviously do the quadratic as well. But usually we're kind of interested in just H, thank you, H plus concentration so that we could get to the pH. Any questions on that? Okay, so we did this one last time, and we did the assumption there, and the assumption was good. And again, just a reminder, as we talked about, you definitely want to make sure you check your assumption. Again, if we have, for example, this same problem, but instead of 0.5 molar, we had 0.05 molar. Again, if we set up our sort of ice table here, like we did in that previous problem last time, it will give us a very similar sort of table. We'll have a 0.05 rather than 0.5. 0 and 0 change will be minus x plus x plus x. And we'll get 0.05 minus x, x, and x. This would go into our Ka expression, which is our products over our reactants, just like we did last time. And that would equal our 6.4 times 10 to the minus 4, which was the Ka value. Putting those numbers in, we do a little x squared over 0.05 minus x. And we assume x is equal to 0 here. And that gives us x squared 0.05 equals 6.4 times 10 to the minus 4 multiplying, and then square rooting afterwards. And that will get us here something like 0.00566. And again, if we check it at this point, we take that and we divide it by 0.05 and times it by 100 to check our assumption. Maybe not divided by 100, but times it by 100. That will give us about 11.3%. And it is a bad assumption. So just a reminder that, again, you should check it. And as you might see, what is the difference? The difference is really the concentration we had in the first problem was much larger, right, than the concentration that we have here in this particular problem. So the concentration you start with, as we'll talk about, is really important in terms of, for example, whether or not the uh, assumption will work. You kind of think of it as like, if you have like a whole pizza and you just take one piece, you still have a lot left, right? Not big changes occurred. But if you're down to like, a couple of pieces of pizza and you take one, then you just lost half of what you had there to start with, right? So the initial concentration and the change that occurs, even though it may be small, is more significant, obviously, when you're starting with a smaller concentration than if you're starting with a larger one. Yeah. That's correct. Yeah. So we do that because we could do the assumption in the first place. We could assume x is equal to 0 because this is a small value of k. And because it's a small value of k, that means that when you reach equilibrium, you should mainly have reactants. And that means the change part, as it's headed in this direction, is going to be relatively small and can be negligible. And that's what you're basically trying to test in that calculation. You can't do it on a large value k because a large value k means obviously you have a lot of products at equilibrium. And that means obviously to get the products, you would have a pretty big change to get over there to that side. And you can't do the assumption in that situation. Other questions? All right. So as we just saw there and we did last time, we will do an ice table for any type of weak acid, and as we'll see as well, weak bases. In most cases, we ignore the ionization of water. So what this means is for all of our calculations, we ignore water's contribution to H plus and OH minus. Obviously, water, when it breaks apart, like in KW, produces H plus and OH minus, right? And in some cases, the concentration from water is actually larger than what's provided by the acid or the base. And sometimes books will go, hey, that's like way larger the water's contribution. So we're just going to go with kind of like water's type of value. So we're going to ignore water's contribution. So basically what that means is any H plus that we see in a problem or any OH minus that we see in the problem, we're just going to kind of assume that it came from the acid or the base. And that's the only sort of contributor. Water is not really going to contribute any H plus or OH minus to our calculations. So you don't have to do much other than what we've been doing, but that's sort of the assumption. But if you do come across it somewhere like a book and stuff, sometimes they will say that, like, hey, like water is greater concentration or much greater concentration. Uh, we ignore the OH minus because it's determined by the H plus. So here we do use an ice table, and obviously it's really the same sort of approach. And we can get our X, which is usually our H plus, and that will allow us to get to our pH. All right, so let's try another one here. We have a monoprotic acid that's 0.122 molar. Ka value is 5.7 times 10 to the minus 4. If you're not sure what to use for a formula, you could just use this guy. That's a generic monoprotic acid because it has one H, right? So go ahead and give it a go. See what. Okay, let's take a look, see how you're doing. So again, you just need a formula. You could use something like that. We know this is a weak acid because we do see a Ka value. So we will set up our sort of equation here. And again, going to head in both directions, going to break apart into H plus and a minus in this case. That'll give us a Ka expression of our products over our reactants there. And that's going to equal 5.7 times 10 to the minus 4. Doing our ice table here, we'll go initially 0.122, we'll go 0, 0. Again, minus x, plus x, plus x. That means at equilibrium 0.122 minus x, x, and x in this case. Any questions all on the table or anything like that? At this point, we're going to go into our expression there, and that's going to get us an x squared divided by 0.122 minus x equals 5.7 times 10 to the minus 4. That's a small value of k, which means we can assume that x is equal to 0. And if you did that, you saw that the check hopefully was bad. Yeah, that's 6.8%. Yeah. So if you went through that and kind of solved it, and you checked it, you would see it's not so good. If you didn't check it, then let me tell you, it's not so good. So here, because our check is not good, we just go back and basically do a little quadratic in this case. So we are going to multiply that to the other side. That's going to give us x squared is equal to 0.122 times 5.7 to the minus 4. And that's going to get us 0.0000. I know I could have wrote some scientific notation, I imagine. Minus 5.7 times 10 to the minus 4x. We're going to combine everybody to one side there, and that's going to give us x squared plus 5.7 times 10 to the minus 4x minus, I wrote all the zeros already. Why not? There you go. Equals 0. So that's going to be obviously our BC. So x is equal divided by 2a. Popping in some numbers here, we'll go negative 5.7 times 10 to the minus 4, plus or minus. If we do the square root part, or inside the square root, that's going to be b squared, so 5.7 to the minus 4, a little squared. We're going to then subtract it from 4 times a, which is 1, times c, which is negative 0.0000695. That looks like inside the square root, 0.000278. You then square root it. Maybe you get a 0.0167, all divided by 2a, which is 2 in this case. All right, so doing the plus first, minus 5.7 to the minus 4, plus what we got after we square rooted it, divided by 2, looks like maybe 0.00806. We do the subtracting there, minus 5.7 to the minus 4 minus 0.0167 divided by 2 gets us a negative version almost of it. Negative 0.0086. Clearly, since we are looking for H, that doesn't look so good. So I'm going to go with this one. And that means that, as we can see from our table here, H plus equals X, which would equal 0. What there? 0.00806. 0.00806. So now we could go into our pH. So our pH will equal minus the log there of 0.00806. And if we do that there, 0.00806, like a 2.09 here for our pH. Yeah. In this particular case, if you just blew right through the assumption and didn't check it, you got a pH pretty close to it, but it won't always be the case. Yeah. Any questions on that? Also makes sense. It's an acidic pH and that's an acid, so that's good. We didn't end up with like a 12 pH, which probably wouldn't be so good. All right, give this one a go. What is the H plus concentration? And well, we also do like the pH as well. Of a 0.01 molar HCN solution, Ka 6.2 times 10 to the minus 10. Okay, let's take a look at this one again. We know it's a weak acid, definitely see a Ka value, so that tells us. So we're going to do our ice table here. We'll have our weak acid break apart into H plus and Cn minus. Going to give us a Ka expression here of our products divided by our reactants. And that's going to equal, we got there, 6.2 times 10 to the minus 10. So initially here, 0.0100, change going to be minus x plus x plus x, and that means at equilibrium 0.01 minus x, x, and x. Like normal, we're now going to put this into our expression, right? So that will get us x squared divided by 0.01 minus x is equal to 6.2 times 10 to the minus 10. Again, small value of k there, so we could assume x is equal to 0. And that will get us x squared divided by 0.01 is equal to 6.2 times 10 to the minus 10. Again, we're going to multiply first and then square root it. And if we do that, 0.01 times 6.2 to the minus 10, a little square root action on it. And we'll do a little scientific notation. Too many zeros to count. X is equal to, we'll go 2.49 times 10 to the minus 6. Again, we do want to check it just to make sure it's okay. We're going to take it again and divide it by what we're going to subtract it from. So 0.01. We're going to times it by 100%. And in this case, I think we should be good. You are not even at 0.1%, so the check here is good. It's like 0.02%. So since the check is good, that will be our X value there. A little bit of rounding. Looks like we end up with number 2 on our list. And that does equal, obviously, our H plus concentration, as we can see. And that also means that our pH here would be negative log of 2.5 times 10 to the minus 6. And that would get us something like, probably not that number there, minus log of, not that number either, that number. 5.60 here in terms of our pH. Any questions on that one there? So again, it does work, but again, not all the time. So you definitely want to check it. As we talked about earlier as well, you can't always just roll with the quadratic. We just rather just do it that way. But this can obviously save you some time. Any questions on weak acids here? All right. Next thing we're going to talk about is percent ionization of an acid, or really even a base. So that was quick talk. Let's go back, talk a little longer. So the percent ionization of an acid or base is basically when you take the concentration of the H plus and divide it by the initial concentration of the acid, and you times it by 100%. Frankly speaking, that is the same calculation as your check that we just did. So when you make an assumption and you're doing your check, you're actually doing this calculation right here, which is the percent ionization. And again, it's believed that 5% or less is all okay. It's not that big of a change that's occurring, but that's essentially what you're doing. Obviously, if you have a strong acid or even a strong base, you will have 100% ionization. It's going to completely break apart. It's a one-way street, and no base coming back the other way. Obviously, in a weak acid or even a weak base, you have more of obviously a reversible type situation. And we see here that what I was talking about earlier with sort of the pizza example, we could see that as the concentration initially of the acid is larger, we have a smaller percent ionization. So it doesn't make as big of an effect on what's coming off. But if our initial concentration was much lower, we would have a much higher percent ionization. And again, back to that example, if you only started with 2 pieces of pizza and took one, You just basically took half of what you started with. So it's a really big percentage of what you started with, rather than if you had a whole pizza, you took one piece, not a big deal. You still have almost all of your pizza still left there. So the change is not that great at that point. So that's why, again, as I talked about earlier, sometimes the assumption will work and sometimes it will not work based on sort of the initial concentration of your acid and also your Ka value as well. So if you want to calculate percent ionization, really, like I said, of an acid or a base, for a base, it would be really the concentration of hydroxide over the initial concentration of the base. So it kind of works kind of the same way. You could just plug and chug into there. Now, if we look at a question like this, which is a solution is 8 molar formic acid and is 0.47% ionized, what is the Ka value? So another sort of application that we could kind of use percent ionization for is a problem like this, since they gave us our percent ionization. So for example, if we want to know what the Ka value was here, we could kind of roll through the calculation like normal. Definitely we have a Ka we're looking for, so clearly this is a weak acid. And that means that we would take this guy and just kind of run through our ice table like normal. It would break apart into H plus and HCOO minus. Now, initially here, we have 8 molar of it and 0 and 0. Change would be minus X plus X plus X. That means when we reach equilibrium, we have 8 minus X, X, and X. This would go into our Ka expression for this, which in this case would be the concentration of our products over our reactants, kind of like normal. And that would equal, well, that's kind of a problem. We don't know what that is. That's kind of what we're looking to find, right? Because normally we would take that equilibrium line and basically put it into there. And obviously you could solve for X or whatever we're looking for. But in this case, we're actually looking for the Ka value. So we have to kind of think about kind of like the experiment we're doing in the lab, maybe a back way to sort of figure out the equilibrium constant value. So we do have one other piece of information given to us in terms of the acid, which is it is 0.47% ionized. And if we use the percent ionization formula, which is percent ionization is equal to the H plus concentration divided by the initial concentration times 100 of the acid, we basically can solve for the H plus concentration. And that would be really helpful because we could see down here, if we look at our table, the H plus concentration is equal to X in this case. And that X is the same X as this X, and it is the same X as this X. So by knowing that percent ionization, it is going to allow us to basically figure out what the X value is in our table without having the Ka value, and that will eventually get us to the Ka value. So if we do that, this thing is 0.47% ionized. We're looking for the H plus concentration. Our initial concentration of our acid is 8 molar and times 100%. So we're going to multiply the 8 molar to the other side and then divide the 100%. And that will get us 0.47 times 8 divided by 100. That is going to get us a H plus concentration of, and we'll go decimal, here's good, 0.0376 molar. So this is not the answer in this case, right? Because we are looking for the actual Ka value, but we can see that the H plus concentration equals X, which means that this value up here also equals X in our table. And that means that that guy's concentration would be 0.0376. So would our HCOO minus there, 0.0376. And then this guy at equilibrium would be 8 minus 0.0376. And that's going to get us here 8 minus 0.376. I get the 6 there. There I go. And we'll go 7.962. So we now have the equilibrium concentrations of everybody. And now we actually do have something that we could put into our Ka expression and get an actual value for the Ka. So if we put that in there, we'll go basically our Ka will equal, get rid of my little line there, I think. So our Ka here will equal up on top 0.0376 times 0.0376 divided by 7.962. That is going to get us here divided by 7.962. Looks like a Ka value of we'll go 1.8 times 10 to the minus 4 in this case. So again, by having that extra piece of information about percent ionization, it allows us to basically figure out the H plus concentration and equilibrium, which in this case is obviously very beneficial as that equals the X value in our ice table, allowing us to get to our Ka. Again, very similar to what you're going to do in part 2 of the experiment, except that you're going to use absorbance values and kind of do and Beer's standard curve to basically figure out the X value. Any questions on there? All right. Now, weak bases also work very similar to weak acids. They will set up an equilibrium, and it will require you to do an ice table when you do it. As we talked about earlier, I would recommend that you maybe do include the water in the reaction with a weak base. That way you could see maybe where the hydroxide is coming from. This is going to set up a equilibrium, which means we can write an equilibrium constant for it. And maybe not surprisingly, instead of a Ka, this is what is known as a Kb value for a weak base. So weak bases will do our Kb, also again, products over reactants here. Now, the Kb value, as it increases, so does the strength of the weak base. Just like we talked about with the weak acid, if you have a strong weak base, it is still weaker than a strong base like sodium hydroxide. But in comparison to other weak bases, as the Ka value increases, so does the strength of that weak base. The reasoning is the same reasoning. The Kb value increases as an equilibrium constant, which means if it increases, larger K value, more products. More products in this case means more free OH minus that's floating around in that solution. And that makes it a stronger weak base than another weak base that you're comparing it to. How do we solve these problems? Well, frankly, we solve them the exact same way as we solve weak acid problems. The only difference is when you do your ice table here and you solve for X. X in this case is the hydroxide concentration. It is not the H plus concentration, which means you typically need to do a little POH action first and then get yourself to the pH. But other than that, it's pretty much done the exact same way. I would say not just for the writing out the equation. Sometimes people struggle with like what it's making on the other side. So a lot of times people will write this reaction with ammonia and end up with H plus on the other side. So sometimes it's easier with bases to make sure you do include it and just know, okay, that's the base, and just think about it, Bronsted Lowry. Then you can kind of visualize, kind of where the hydroxide comes from and stuff like that. It is still a water and it's still a pure liquid, so it won't be included in any part of the calculation. Other question? All right. So yeah, it's just like this guy's yelling to get the OH minus concentration rather than the H plus, and then obviously like we just talked about, get to the POH and then to your pH. Here's the table from your book. Again, you may have to reference some values for Kb. Kind of just like strong acids, strong bases do not have a Kb value, again, because they're not going to set up an equilibrium. They're just going to break apart. So if you again see a Kb value, you can safely assume that that thing is going to be a weak base. Also, like we talked about, pretty much most of all your strong bases are going to come from group 1 and group 2 on the periodic table, and actually have hydroxide in the formula. So most strong bases will actually have hydroxide in the formula. Most weak bases are a lot of times nitrogen based. So you see a lot of nitrogens in the weak bases. They're amines and organic chemistry, and they're actually where a lot of weak bases sort of come from. All right, let's try one more here to wrap it up for today, I think. And the amine compounds often have a pungent smell. The Kb for C2H5NH2 is 5.6 times 10 to the minus 4. What would be the pH of a 0.15 molar solution? So let's see what you come up with here. All right, let's take a look, see how you're doing. So we know a couple of things. Obviously, this is a weak base since we have a Kb value given to us. So we might as well start with the equation. So as I said earlier, sometimes it's, probably good to put the water in with these weak bases when you're dealing with it. And again, it's going to accept the H plus there from the water and basically just going to add a hydrogen at the end of this and a plus because it does gain the plus as well. And that is, again, where we're going to generate our hydroxide from. It's going to come from the water in this case. That will give us a Kb in this case of our products over our reactants here. And that's going to equal our 5.6 times 10 to the minus 4. Doing our ice table here, 0.15, 0 and 0. Obviously, water not included in anything, so just going to leave it blank so I don't tempt it to do anything with it. We're going to put it here to our equilibrium, 0.15 minus x, x, and x. Any questions on the table there? Like normal, we're just going to roll this into our expression here, x squared basically, 0.15 minus x equals 5.6 times 10 to the minus 4, it says. It is a small value case, so we could assume x is equal to 0, and of course you checked it because you are professionals and know it's 6.1%, not so good, right? So again, we'll have to do a little quadratic here. And we again are going to just multiply that to the other side, and that will get us here. X squared is equal to, not a good day for assumptions apparently. Let's see, 10.15. 0.000084 minus 5.6 times 10 to the minus 4x. Bringing everybody back to the same side, going to get us x squared plus 5.6 times 10 to the minus 4x minus 0.123484 equals 0. That again is our A, B, and C. That's going to go into our quadratic. Good practice, maybe. We'll see. X is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. So popping in some numbers here, minus 5.6 times 10 to the minus 4 plus or minus. If we kind of take care of what's inside the square root, we're going to go 5.6 to the minus 4 and square it. Minus 4 times 1 times negative 0.000084. Looks like maybe 0.000336 inside. Taking a little square root action, a 0.0183, all divided by 2 times a, which should be 2. Again, going to give us here our two x values, negative 5.6 to the minus 4. I'll do the plus first, 0.0183. Divided by 2, going to get us an x value here of 0.0, too much close over. X is equal to 0.00889, we'll call it. And if we do our negative, that's probably not going to be so good for us, I don't think, but we'll subtract 0.0183. I'm seeing a negative number there, and we'll get a negative 0.00943. Clearly, we could outrule the negative. We do want to remember, though, that X here is, again, not the H plus concentration, but it is the hydroxide concentration from our table. So this X value is equal to the hydroxide concentration. So we can go into our POH in this case. So our POH is going to equal minus the log of the hydroxide, which is negative log of 0.00889. And that's going to get us minus the log 0.00889. Looks like a 2.05. Now, if for some reason you thought this was the pH, it really shouldn't make sense to you, right? Because we're dealing with a base. And clearly, if you thought 2.05 was the pH answer, that really definitely shouldn't make sense to you. So it is not the pH, it's obviously the POH. So we need to do our last little step here, and we'll just go here to do it. pH is equal to 14 minus the POH. So our pH in this case would be 14 minus our 2.05, giving us a pH of 11.95, which does sound very basic since this is a base. Any questions on that? So again, works the same way, weak bases as weak acids. The only difference is, again, you get the hydroxide at the end rather than the H plus. So the additional step, again, that POH and subtracting 14. Any questions on that? Yeah. Say one, which one again? I'm sorry. The 0 point, which one? You got it? Okay. All right, there, that is from the square root of what's inside. Yeah. Other question? Okay. We'll lay it up there for